Okay. Good afternoon, good morning, and good evenings for everyone, wherever you are. Today's knowledge sharing, we will continue on the specific subject, go through overview of hydraulic fracturings. Actually, this is kind of literature review adapted from or adapted with modified from the number of learning symposium in the past. Uh, and first of all, thank you very much. It's a real pleasure to be on this occasion. I hope everyone enjoys. Then I have to say, I hope we have learned something along the way. But let's go ahead and kick it off. Okay, we are going to have a brief outlines, and one of the real challenge for everyone here was how do we take three number of this call, of course, from the literature review and condense it into 1 hour where it makes sense. So I'm going to have basically a brief introduction to hydraulic fracturing. We're going to talk a little bit about geometry and azimuth. And then we are going to really get into why it is so important. You know why is conductivity is also important then because you are not just buying a fluid or and proppant, you are buying the whole that get that oil and gas to the wellbore. We are going to talk about how to select the fracture proppants because again, if you don't get it right, you don't get have anything. Then we'll talk a little bit about quality assurance, quality control. Then basically we will sum it up. All right. Hydraulic fracturing, basically, in layman term, it consists of blending, carrying fluid special chemical, and those chemical may be something along the line of chelating agents, biocide, oxygen scavengers, scale inhibitors, things that we need to enzymes too. You know, to make the fracture fluid do what it's need to, and then the proppant. Once we get the blended fluid through the blender, we actually pump it down into the pay zone at high enough rate. The pressure actually hydraulically fractures the rock. Now, as we continue pumping, the pressure, which are above the fracture gradient of the rock, create a width that extend the fracture out away from the wellbore hydraulically. And it can be pumped via casing, tubing, or tubing casings annulus. The path of fracture based of fracture treatment basically consists of three main components. The first is pad is very important. This is net fluid, meaning that it's contain no proppant. It is usually the main fracture carrying fluids. It is a pump to control the leak off because you got to remember that we are pumping this fluid into the porous rock medium. So we are pumping in at this high pressure. Some of that fluid is leaking off into the rock. Okay, so we initiate that fracture. The reason is to so important is it is impossible to propagate a fracture with proppant-laden fluid, and the reason for that is because the proppant is rubbing up against the wall, the rocks, it will breach. So if you pump too much pap, you are wasting money. If you don't pump enough, your job will end prematurely. So we will follow the with what we call the slurry. It's blended fracture fluid. It's got the proppant agent. It's usually high viscosity, meaning we use a guard derivative to increase it up to several hundred centipoise. But it can also have lower viscosity like linear gel, which is a non-cross links, somewhere in order of 20 to 40 centipoise. And in a lot of cases, like you probably hearings on shale. We are water frac. Basically, it is few other chemical, but the majority of it is a fraction reduced in water. And we follow that with a flask because you have to get the fluid in the wellbore, push it into the formation. Now let's talk a bit now about fracture geometry. Um, there are several factors that affect fracture geometry. Number one is well spacing. What is the estimated versus the actual drainage area? The worst things that you could do if you are in a 40 acres competitive lease, if you frack it into neighboring lease and drain that lease, there has actually been litigation proposed of something called relative damages. And so you want to know what is spacing and how to to design the proper fracture length that you see up here. Fracture length is really the volume of fluid pump is what dictates it. And the volume of fluid remain meaning the fracture, because again, someone leak off, someone not the geometry of the fracture. Next, fracture width and height. Width and height are controlled by viscosity of the fluid, the injection rate of the fluid, and the in situ stress of the rock Mother Nature has put there. So when we look at the fracture length, there are many factors that influence it. It's going to be dominated through by the total volume of fluid pump versus the volume of fluid remaining in the fracture. If you given a constant coach rate in the formation, then the length of the fracture is going to be primarily controlled by the injection rate. When we look at the fracture width, it is primarily controlled by the viscosity of the injection fluid. Now it has some control by the Young modulus of the rock as the function of viscosity. It is affected by lesser degree by the in situ stress, contrast, and rate. But all things being equal, again, length is going to be controlled by the rate, width is going to be controlled by the viscosity. The fracture height is almost primarily controlled by the in situ stress. And those rock above and below zone of interest, again, to lesser degree by rate and viscosity. But if you have no stress contrast, then you will go into that a minute. If you have no stress contrast, your fracture, instead of being long, will be more shaped like a penny. Here's actually an example. This is Marcellus Shale well that you can see at the left, the profile of what we are talking about. If I draw area here, look at this. Basically, we can see on the bottom that is very, very high stress line. Then you have that area in yellow is the lower Marcellus. And so this is actually a model within geometry of how the fracture change. We can see in the white of the top, there is very, very, dense line. And so the practice actually content it's bounded. As the stress change a little bit, so you see minor variation in width. But again, it's pretty well dictated by the properties of the rock. The most important fluid characteristic are to a number one, fluid loss. If you minimize that fluid loss, that you are going to increase your fracture volume for a total given pump volume. Okay, on other one, viscosity, it's a friction loss, fracture area, and fracture width. The most pressing factor here is it affect your proppant carrying capacity. The reason for that is the proppant turn into the corner, gravity will take over. And this is why when we are trying to get this along the frac in tight sandstone, like the Mesa Verde or Travis Peak, Cotton Valley, something like that, then in that case, you got to have the viscosity to carry the proppant out that several 100 feet from the wellbore. Without it, it will fall out and it will breach shell and a little bit different. We actually it is tumbling effect, but because we are pumping slick water, we can actually move the proppant out into the cell. If you look at the left hand side, basically see what it look like here is a fracture. You can see that with pumping in progress, the fracture is open and it may be a half to 1 inch wide in width. And you can see the shell barrier. And then once we have pumping the fracture, Mother Nature pushing it on it with stress, it will actually to try to close. It is the proppant that we put in there that keep that fracture from closing. Without the proppant, at fracture will not only close, but it will seal back up. Continues a bit. We are talking about the azimuth. And this is an important one because the orientation and direction of propagation for hydraulic fracture really depend almost entirely on the stress orientation of each individual formation. That's both vertical and horizontal, because depending on what the stress orientation, it will dictate the compass heading that frac will actually head out on. And I'll show you why it's make a difference. Mother Nature, when it's laid down, we have vertical stress, which a lot of people call the overburden, but we also have maximum minimum horizontal stress. A fracture will always propagate perpendicular to the minimum horizontal stress. You will see that in just a minute. When we start looking at the stress, if the vertical stress is less than lateral stress, as you can see in the picture, your fracture will be horizontal. Several years ago, a lot of people didn't think that a fracture could actually turn horizontal because of microseismic and some mind bags things that nature and testing. Then we actually know how, especially in the shallow well, less than 2,500 feet, in many cases, fracture are almost horizontal. In the least principal stress is between the vertical and horizontal, then you actually get an inclined fracture. And the greater that difference will depend on if that fracture is tilted 5 degrees, 55 degrees, or 85 degrees, but they actually twist. And then finally, when the lateral stress is less than vertical stress, which is the majority of what we see today in our hydraulic fracturing, you actually have a vertical fracture. That doesn't meaning to that if you are fracking that you hit a change in stress orientation. That frac can actually turn while it's being pumped in progress, and we have seen that on many occasions. So again, it's propagate perpendicular to the minimum stress, and I have been here the 3 stress axis with a vertical wellbore, and basically we can see here the frac is going to frac perpendicular across the minimum stress. And this is why on a lot of these shale wells, they are doing on work to figure out what is the stress R, because they are doing multiple stages per well. So it's become very important. Now, what are the sigma vertical? When the sigma vertical is greater than sigma h, 1, 2. So in other words, your overburden is greater than the lateral, but the H1 and H2 are very close. Then you got what we call multiple planar fractures. In other words, you may hear today is complex fracturing. This is what happened in shales like Marcellus, Barnett, Fayetteville, where you see that really orthogonal fracture pattern that has become to be so indicative of many of the shale. We also look at transverse fracts. and later we will see another longitudinal frac. When you hear about drilling 10,000 foot lateral, let's say in the Eagle Ford, with 25 stages, what they are talking about is exactly what you see in this picture. The horizontal wellbore is drilled perfect or parallel to that minimum stress axis. And then this is transfer fracs actually just chop across the wellbore. In some cases too, when we actually in the Bacon initially started, when we are doing initial well, then Richland County, Montana, fracturing technology had no progress to what is today. And that case, initial well were actually done with what we call longitudinal frac, where the wellbore actually drill in direction of the maximum horizontal stress. And then at the point, the fracture actually lines up, the wellbore straight up and down, move forward. So why is it important to really know it? Well, in a tight or low permeability formation, it can actually cause significant problem, not only with the reservoir recovery, but also interference between the well. So what you see here, here is a hydraulic fracture on well number 1, and this is just basic pattern. We can see if we drill wells, number of well, then we frac this well, and it's not 60 degree, not 60 south of the fracks really line up what you are saying here. You're getting excellent reservoir coverage, and you are getting the maximum drainage and recovery. But what happened now if the fracture pattern is still drilled on the same 160-acre well pattern, but now the fracture azimuth is north 80 degrees east. And in that particular case, we see the frac coming in the north, okay? But now look at, you got interference between the facts that you can actually see this one wheel shot, but the biggest deal is looking right here in the middle. That is an incomplete reservoir drainage. This operator would actually have to drill a fifth well in the middle if they were going to properly drain this reservoir. Disastrous well location azimuth. What if that azimuth was actually 90 degrees? And when I say look out tanks, here it's come. This has actually happened on numerous occasions during the frac job. People have actually fracked into another well, and things to remember on one occasion, actually on the job, we actually not only fracked into the wellbore, but we also fracked through the Christmas tree and actually blew out on the stock tank. So it can have a disastrous effect if you don't do your homework properly. Today we talk about a lot horizontal drillings, big benefits, larger area of contact with the wellbore. You are saying this isn't just every shale, especially like the Bacon, Eagle Ford. You're looking at the well with lateral in excess around 10,000 feet. It minimizes your fracture head growth, and you have less environmental impact. You are drilling multiple wells. So what we are trying to say here, the vertical well, you got one wellbore, one drainage pattern. If you drill in longitudinal, again, you are still drilling one well, then you are getting one drainage pattern. The beauty of technology today is that it's transfer fracs, as we show here. Now, one footprint and one multiple frac. And in a lot of cases, especially in the Marcellus, in the western side of Colorado, up in North Dakota, they're actually drilling directionally multiple well from one pad and going and doing frac on each one of them. So your environmental impact have even become less. If you look at here at the wellbore orientation, This is what kind of demonstrations, as we can see here, that here is the horizontal lateral, and you can actually see the transfer fracs, they're straight up and down, they're along the wellbore. If we move over, then we look at an oblique frac. This would be if only actually drill the wellbore not parallel to the minimum and not parallel to the maximum. But say you drill a half in the between, then you would actually have a pretty big fracs that will initiate and turn, because of Mother Nature ultimately dictates what is going to happen. And finally, here's kind of little drawing of longitudinal frac where they come in and done 5 fracs. But again, your reservoir drainage is quite a bit less. If we look at now at fracture conductivity, and now we are starting to get into, okay, we have pumped our frac and we got it out there. So let's talk about the conductivity. Why is it so important? And basically, all the conductivity is the symbol in the fracturing industry is WKF. WKF. It is the width of the fracture in feet times the permeability of the fracture in millidarcy. So it is measured in the millidarcy feet. So along this line, picture downtown when you are out there on the edge of these things, picture yourself on the 2-lane road in Wyoming and you are doing 70 miles an hour and you are heading into town. But again, there is no traffic. As you get closer into downtown, things start getting more and more crowded. And many cases, if you are in a car, you might end up slowing down on the hydraulic fracture. The absolute opposite happen as you get in a constant pressure situation. As you get closer downtown or the wellbore, things start speeding up. They speed up rapidly. So if you don't have good conductivity right there at the wellbore, then basically you create a choke point, and it actually can quite often does limit the production that you can get out of one of this well. So knowing that we need conductivity to really get the maximum production rate, which dictate directly to the maximum recovery, how do we go about selecting the proppant to make sure that we accomplish our task? We look at in everybody said, well, what's the ideal proppant? And I got a list here. You crush resistant, you want to be deformable but not brittle. There is, you don't want it to embed into the walls of the formation. I highlighted readily available because today we are in the one of the greatest proppant demand shortage literally in history of the industry. Many industry experts expect to get way worse before we are going to start to see relief. The season for that is it takes time to ramp up mine, to get a new mine or to expand the mine to meet the demand, which basically just exploded. What I want you to take away from this slide actually is the ideal proppant meet all of these criteria. There are really is no such thing being an ideal product. It just doesn't exist in the real world. So you look and you say, well, which product do I choose? There is alpha quartz, and notice here that I don't use in word sand. Sand is the geologist sand. Is a size term, means that you fall between a certain millimeter range. What we are actually mining and pumping into this well is alpha quartz. And so the mining companies refer to it as alpha quartz proppant. Now you can take that alpha quartz proppant and you can put in resin on it, which does several things, but primarily it's greatly increased its strength. Or you can actually manufacture a ceramic. And if you notice here, there's some overlap. There is overlap between all of the three, and there is no reason for that. If we look at the categories of propane on the x-axis, you see increasing performance properties, but we keep this in mind as you go to the right performance increase. So that's cost. On the left, you have your what we call net closure stress, and it increased from 0 above 13 pounds. The lowest of the cheapest that you see alpha quartz and is the green bar, and you notice it goes from 0 to 5,000. The reason for that, because above 5,000 pounds, northern white sand start to crash, and it starts to crash dramatically. And a little further into this, you are going to see what that actually does to your well. Next, on the list, we go to the recent quoted alpha quartz. They are intermediate and premium grades that you can see. You know, some of the premiums get up to 11 and 12,000 pounds of closer stress again. They are quite be more expensive. Has that come the family of ceramic, and those will be any range from the economics, lightweight ceramic, your intermediate, and finally all the way up to bauxite. These are all considered ceramic. And finally, the daddy king is of all this is resin coated ceramic. They are strongest material out there. They are also the most expensive. If you look at the alpha quartz, you are looking at about anywhere from 8 to maybe 10%, 10 cent a pound that wellhead that is, you know, takes into consideration selling it from the mine, all the transportation costs, and then the service companies profit margin as well. By the time you got over the resin coated ceramic, some of these are above $1.10 to $1.15 a pound at the wellhead. So when you come 10,000 or excuse me 3 or 4 million pounds into the wellhead, you know, have huge expand and millions of dollars just for the propane. If you look at this line, just flash across your screen, you will see that 5,000 pounds, you intersect 5 different propane. So which one do you choose? You got to have finite versus infinite conductivity. Information permeability plays a big role in this section. And the reason for that is that more finite conductive fracture is the more pressure drop you will have from tip to the wellbore pressure is all you have to move. So the more pressure you lose, moving that oil and gas down the fracture, the more restricted your rate will be. And basically, when you say a fracture is infinite conductive, it means that there is negligible pressure drop to move the oil and gas from its entry point to the wellbore. Depth and closure stress, this is how most people pick propane, and going to see in a minute that's now the way we to do it. Formation duct tape, that filthy and embedment more ductile formation. First of all, the harder it's to initiate fracture, but also the most prone it is embedment median particle diameter. You are going to see that this make a huge difference in how we select a proven cyclic stress. Every time you start a well to increase it or decrease it, your cycle that propane multi-phase flow. Most well don't produce only oil or only gas or only, you know, they produce a combination. Then, of course, there is something called non-Darcy flow beta factors, which is from Forchheimer's equation. Mobile finds, when we talk about finite versus infinite conductivity, mobile fine reduce your propane conductivity, of course. The source for mobile fine, there are really 3. The first one is, of course, propane crushing. You crush the proppant, it's going to splinter, it's going to fragment, it's going to move. The second one is erosion of the fracture face. As we pump these fractures, you're going to erode some of the fracture face. It's almost like sandblasting. And the last one is spalling. Spalling is associated with a proppant particles embedded into the fracture face of the rock. Those fines that are created called spalling. Pore through diameter effects is very critical. If it's greater than 1/3, it's other words, if the particle that is trying to invade the pack is greater than 1/3 of the pore through diameter of your proppant, it will breathe instantly. It will not enter your pack. If it's less than 1/7, it will flow through. So the problem is if it is between 1/7 and 1/3, it will not enter the fracture, but it will enter the fracture and will plug your proppant bed. This is basically on the left is what I'm talking about, what we are talking about. This is a hickory sand at 8,000 pounds of closer. And you know, if I have looked, there is not single grain here that is not fractured, shattered, completely crushed, shredded, or whatever. But if you look at the basketball and marble effect, you have destroyed your porosity and thus your permeability of the fracture meat. On the right, you see premium resin coated the same 8,000, and you notice that porosity and permeability are maximized. You see one grain right here that is fracture, but you notice that it didn't move. The reason for that is because the proppant resin coat keeps proppant intact. And I can say the next one, enough, never attempt to choose a proppant based solely on depth and closer stress. You have Northern Light sand like Jordan, St. Peter's, St. Simon's want to work. Brown sand are now typically in hickory bread. Look at the river deposit. The Northern Lights begin to crush it 4 to 5,000 pounds, but the browns typically begin to crush at less than half of that what we see in many cases today. You are actually pumping sand where they are not supposed to be, so always pump your proppant. And here I want to show on the left, I want to, if you got two 2040 ceramic at 4, 6, and 10,000, you can see the stress increase. Then basically the width increase, okay? 240 ceramic at 4, 6, and 10,000, you see the stress increases, then basically the width increases, okay? On the right, you have 240 Jordan, which is Northern White at 4, 4 and 6, and then you notice again it's increasing. Then you have on the bottom to 2040 resin coated quartz at 1,000, and you don't see any embedment, of course. The reason for that, the resin that goes on, that is pliable, it's begin. When what I want you to notice here, look at the 2040 at 4,000 psi. We still see how nice and round it is. Look at the 6. The reason you are saying this jagged, irregular end is because the proppant has already started to crush. Sorry. SPE 84,204, one of the selected paper that I use reference. This published paper was done many years ago actually, but still holds true where it's talk about the variation in particle. Shift distribution can have twofold swing in the fracture of conductivity. Now, what you see here on the left point, 443 543 pointer right 0.71. This is your average particle diameter. And if you plot of this and you look at the ISO spec, both of these propane are ISO compliant. They are both fall within 90% or more within the SIP screen for this 20 or 40. And they got two different median particle diameters. Look at what happened to here on the conductivity. 0.16 or 17 millimeters is all the difference that you are having here. It's almost infinitesimally small that you could even show with your finger. Yet you got complete twofold reduction in conductivity just by shifting the median particle diameter from left-hand side, that shift distribution to the fine side of the shift distribution. Let's talk about propane quality assurance and quality control. And then we all kind of sum everything's up. That will give us plenty of time for question and answer. When you look at the proper performance, you have data that design that define from outside practices, and these are established by governing bodies. ISO stands for the International Organization for Standardization, and the guideline is published in publication number 13503 13503-2, and the old and the now RPI recommended practices is 19. See, the old API RP 56 is no longer supported by the industry. Everything now need to be ISO compliant. If the data is not established by those guidelines, and basically it can always be excused as non-representative. If you have non-ISO data and testing cannot accurately be compared to what I mean, testing cannot be compared accurately to anything you get out of the laboratory model. And last design for specification is giving you kind of some ideas about some of different things that we need to look at. Hold the propane companies accountable. Make sure to have their facility, make sure they have ISO compliant, make sure they are doing proper sampling, seven analysis, because in many cases the operator is end user of the propane. But the bottom line here is that if you go through the guideline, you not only hold the supplier accountable, but basically make them help you. They know they are propane better than anybody in the world, and they can help the operator and the service company pick the right material. And if you do that, you are going to have the right properties. And of course, you are going to from there, and that you are going to get the right conductivity once you pump it down the hole. And ultimately, of course, you are going to get a very best production. When we look at the propane supply chain, you see here cost with the arrows going increasing one way and quality are going the other way. And you start off with the mining company, and what they say is the quality is the highest when it's the mining company. It's also going to be the lowest cost. Like there may be a manufacturer. In other words, the mining company may not be ultimate manufacturer, especially in a resin coat, or somebody may mine the propane and bring it to the company, actually size it, dry it, and manufacture it. And then finally, it has to be transported. And that usually involve other carrier, whether they be truck, railroad. In some cases, the mining company, the manufacturer, the transporter can be actually be the same company. Not too often, but in a lot of cases, yes, it is. From there, it crosses a line at the point, it goes to a pumping services company, and finally to the operator of the well. What makes this so critical is that, again, The proppant is never going to be as good as it was mined, served in silos. So if you don't do the quality control along the way to make sure that proppant is handled correctly, you can do a lot of damage to it. And basically what it means is that as you move away, you go through different handling procedures, you go to the pumping services company, you look at the margin, your cost is going to go up. But the bottom line here is that the mining company doesn't do its job. By the time it gets to the operators, well, he hadn't got a prior. So what do you do? Well, we can assume a quality and things we are all know what assume spell that that doesn't get you a very many results. The next step up, that is what we call storage pointing testing. People will actually go out, they will actually test the proppant at the storage silo before it is does it final one or two translate onto the big one, okay? But it look very good. It passing spec and everything. So I think we are okay. Past that, you move a little bit up those stairs toward that a big dollar sign. You know, you get what they can call well site quality, and this is where people on the actual frac job hire consulting firm, and there's some good one out there that actually specialize in quality controlling the proppant as it come out of the sand king or the mountain movers, depending on what company you are talking about, into the blender. But they also look at the fluid that you are pumping, and they are making sure that everything is being mixed and pumped according to the specification. Uh, Last well site proppant performance, this is where you are going to get your maximum value. Start to quality controlling that proppant from the day it's made. Follow it, look at it, talk to the supplier, see how it's worked. Because if it gets to the wellbore and it's not right at the point, if you don't abort the job, it's too late. One that proppant is goes down to the hole is there, and you didn't get any chance, and that's what make fracturing so critical. When it's come to Q quality assurance, quality control, is you get one shot at this, and if you don't get it right, you got a huge investment that's on the line. So which proppant do you choose now? It's tough choice. It's really is, but there are a lot of people out there that can help. Again, I can't say it enough. I see this every single days when we talk to the engineer frac supplier in industry, is that ticket straightly on depth. It's in closer stress. At the beginning of this sharing, you show a whole list of things that need to be considered. And the best advice we can give to anybody that you choose wisely, okay? Because if you, again, if you choose the wrong proppant, you are dead in your truck. So to sum it up, real briefly, proper hydraulic fracture design and proppant selection to get the right azimuth, get the right fluid, the right conductivity doesn't just happen. It takes engineering. It takes input from the geologic team. It takes knowing the formation, so you understand the direction to drill, the direction to frac is going to go, and that you got the right proppant, because some of these shale wells that we have today are going to the last over 40 years, longer than just about most people carrier. And so that proppant that will we place in there, and the fracture has to, in most cases, has the life of the well. And again, there are many factors to consider. The best advice we can give anybody in each well is unique and should always be designed based on those individual well parameters. Modeling and expert advice from the fracturing companies, from the proppant companies is essential, because you have to get it right. And I'm going to leave you with this one thought. The end of the day, the horsepower racks up and move off location. They take it to another well. The fracturing fluid is broken, float back, and discarded and removed from the location. The only things that you have left is that proppant bed, and it's still you are the productivity of your well, then the life of your well depend on it. So it's make real sense here to select it correctly, design your hydraulic fracture correctly, do your quality control. That basically kind of share today's sharings. We are right on the time, I think. About 15 minutes, so we got plenty time for some question. Thank you very much for the listening. So, this is question number one. I think we capture from the participant, one of the participant. We do have quite a few questions actually. Let's imagine that about, let's start with one way back when you are talking about different direction of fracture and bedding plane. The Antoinette who may possible prefer as if a horizontal fracture follow the bedding plane, does it go farther than an inclined or vertical fracture? Very good question, actually. In most cases, no. And I mean, you can extend it, but when you are fighting the overburden, you got horizontal fracture. What you are going to see is all things being equal, your pressure, your surface pumping pressure will actually be much higher in many cases. The fracture gradient, which is the fracture pressure divided by depth, is actually give you a gradient in pound per square inch per foot, will be well in excess of 1.0. Again, very, very high. They will propagate, they will go out, but it is much more difficult to get along reaching fracture if the fracture is actually turning horizontal. Another question, is there any Venturi effect that make the speed increase as it nears the city? I think this question related with one of the slides showing earlier. It's not a Venturi effect, actually. It is what we call near wellbore or tortuosity effect. Again, this is not a Venturi effect. It's what we call a near wellbore or tortuosity effect. As if you were to look at the pressure profile of the pressure drop from the edge of the reservoir through the fracture into the wellbore, what would you say is in most cases of 50% of the pressure drop actually occurs within 20 to 30 feet of the wellbore. And what it is all of, you got given volume, well, that given volume in the reservoir way your real extent is greater. Now you are starting to move that some volume into much more confined area, and you got not only four grains in the formation, but you have particles in the proper portion of hydraulic fracture. So it's not really a Venturi effect. It's the fact this particle are having to speed up if you were to go back and reference for the Siner's equation, for Siemens equation. And this is something we get into the three uh, 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 days of school. But if you go back and your reference for Siemens equation, there's actually line density term, and there is a velocity term. And the velocity term that is called non-Darcy flow, actually what we can cause of this restriction, because now the velocity of the fluid, again, same volume, smaller area, therefore speed has to go up, become dominant. Okay, this is the next questions. who is interested in fracturing job that are performed somewhat near a casing shoe, and she wondering, are there other things that we can do in your planning or your modeling of the fracture to prevent or minimize damage to the casings or casing cement from the vertical fracture? If you go back to the slide where we have discussed earlier, earlier this presentation, length is dictated by the ray height, is dictated by close of your stress. You can, if you go back and you look at adjusting rate, adjusting viscosities, what you see, if you are really don't see much change in H, chances are if you are fracturing near the shoe, you are not in high stress contrast, that fracture will grow down around that shoe, and may actually, because these cracks are, symmetrical opposing swings, may actually in some cases go under the shoe and link up across the wellbore. That doesn't necessarily mean that you are going to damage that shoe. If you were to try drill out, then you may actually drill into the fracture area, have some communication issue. But if the well is properly drilled and properly seen in it, it shouldn't matter if you frack around the shoe. You people done many times actually. The next question, okay. When you are talking, when we talk about how do you detect if your damaged casing show it, well, you would maybe get a leak. I mean, sometimes actually we've seen cases where people will go in and drill out their shoe, that they will drill out the float collar all the way down to the float shoe. And personally, I don't recommend that leave the same man in the pipe. Okay, it's going to basically that you are only talking about 40 feet. That's nothing when it's come to the fracture head. It's very rare that you are going to, if I understood that question correctly, damage shoe. Okay, but again, it goes back to the well design. Make sure that you have good cement job, because the same at this job is that zonal isolation is going to keep the fracture where it needs to go. I think that's all for the question that we have at the moment. Again, thank you for the listenings and hope you guys enjoy it.